Hello physics students. Today we're going to analyze what happens to light when it goes through multiple layers of optical material. Now a common example in physics problems is you've got water and on top of that floating some oil. And then the light starts in the air, goes into the oil, and then goes into the water, refracting every time it goes through a barrier. Another common example is lenses that have an optical coating for reasons for some particular reason in photography. They put a coating, so then the light goes through the coating, then the glass. But we're going to look at this example I made up with basically 4 different materials. Well, 3 different, but 4 layers. We've got air here, zircon, lucite, and air. And I put the indices of refraction of each. The light comes from the air, and let's suppose it comes in at a 73-degree angle here with respect to the normal. Once it hits the zircon, it'll refract. Then when it leaves the zircon, goes into the lucite, it refracts. And then when it leaves the lucite and goes into the air, it refracts. So it bends at every boundary. Now, we're going to go ahead and calculate all these angles. But I just want to say that sometimes on the Regents, when they ask a multi-layer refraction problem, they don't even ask you to calculate anything. They only ask you to either sketch or recognize the correct pattern of the light ray. And so here are the concepts first before we look at the numbers. The laser, if this is like a laser pointer, it goes from air to zircon to a higher index. As we learned a couple videos ago, when you go to a higher index, that means the light bends towards the normal. So we see instead of continuing along on a straight line, it bends pretty dramatically because of the difference in the indices. Now, when this comes down through the surface after refracting and hits this surface, notice these 2 normals are parallel to each other. That means that these 2 angles are the same. So ultimately, we're going to calculate this around 30 degrees, then this is around 30 degrees, the same angle. Now it comes here and strikes this material. Now we're going from zircon 1.92 to 1.5. So we're going to a lesser index. So instead of the light going in a straight line, it'll now bend away from the normal. Smaller index, larger angle. However, you have to know that it will not bend as radically as the air because the index of air is 1. This is 1.5. So it'll bend away from the normal, but with an angle somewhere between this angle and that angle. And we're going to calculate it's going to come out to around 40 degrees. Now when this basically comes down, again, these 2 normals are parallel, so this angle and this angle are both the same, so this is around 40, then this will be around 40. And then when the light strikes here, it refracts again, going from the lucite to the air, and because we go from a high index to low, it bends away from the normal again. So the pattern is towards the normal, slightly away from the normal, and away from the normal again. And basically, from Snell's Law, we're going to see that the smallest angle will occur in the biggest index, and the biggest angle will occur in the smallest index, and anything in between is in between. So again, sometimes multiple choice, Regents question, multiple layer, and you just have to pick, is this the pattern? Or maybe they give you like this, and then towards the normal again, and the smallest angles here, so on and so forth. And you would just pick the right pattern, be done. But sometimes they ask you to calculate, so that's what we'll move on to in a second. But let me create a pause and allow you to copy this down. Now, you don't have to sketch these exactly, but draw this diagram big enough. If you really want to draw it with protractors, the angles, as you could see, are about 30 degrees here and about 40 degrees with respect to the normal, and then 73 degrees again. But you don't have to draw it accurately. Just try and draw it conceptually to the right pattern. It doesn't have to be done to the exact degrees. So go ahead in the pause that I'm going to create, write these notes down. All right, so now let's go on to calculate all the angles. And to do this, what you're just going to do is use Snell's Law at every boundary. So it's 3 Snell's Law problems, 1 here and 1 sine theta 1, so on and so forth. Another Snell's Law problem here, another 3 refractions we have to solve. So let's begin with the air in the zircon boundary. we begin with Snell's Law. I'm not going to bring the reference table up to the camera, but you know where to find it at this point. N1 sine theta 1 equals N2 sine theta 2. The index of air, 1. The angle in air, 73. Index of zircon, 1.92. Unknown angle. We do the algebra, take the inverse sine, 29.9. The next, so now, as I said, this 29.9, the light comes down, strikes here. This is 29.9. So the refracted ray angle here becomes the incident ray angle here. Both the same angles, so we move on to our second refraction here, which is between zircon and lucite right here. And now we have not N1, but N2. We're starting in material 2, N2 sine theta 2, and we're going into material 3, N3 sine theta 3. So we just kind of rewrite Snell's law with different subscripts, but it's the same equation, just to be consistent with our problem. So we do zircon index, zircon angle, and then lucite index, unknown lucite angle, divide by 1.5, inverse sine, you get about 39.6. So I'll create a pause and allow you to copy these notes down. Okay, so now we have one more Snell's Law problem right here. Now, let me just say, I'm going to erase this, but I just want to point out that what we're going to find here is that when we return to the air, even though I labeled this theta 4, it's going to come out to the same same angle as the original 73. Because we return to the same index, we're going to return to the same angle. So notice this ray and this ray are parallel. In the end, it's as if the layers weren't even here. The light is it's displaced a little bit, but it's going to be parallel to the original. So that's the pattern we're going to see. Let me create some room for our next calculation. Okay, so there it is. I do N3 sine theta 3. That was in the third layer of lucite, and then N4 sine theta 4, that's the air. Plug in the lucite data, the air data with the angle unknown, and we get the original 73-degree angle, as I mentioned, which was the original all the way at the top before any refraction occurred. So let me create a pause to give you a chance to copy this down. All right, well, so we learned the concepts behind multilayer refraction, how the angles change throughout, and we learned how to analyze and actually figure out what the angles are, not just conceptually. But I just want to, before I conclude, just point out some patterns. So maybe I'll make room here. So if you put all the equations together in their totality, this is what we just did mathematically. So this was our first problem, this was our second problem, and this was our third problem. But if you, as I said, put these all together, you can realize an interesting shortcut that you might be able to utilize in a particular problem. Let's relabel this A equals B equals C equals D. Now, as you know, I forget what it's called in math, the property, but basically if A equals B, B equals C, and C equals D, then you can conclude that, for example, A equals C, or A equals D, or B equals D, or so on and so forth. And what that means is that if we were asked what the angle was in the lucite, remember that was the third layer. So we had air, zircon, I erased the diagram, but you have it in your notes, lucite, and air. So let's suppose the problem said, okay, gave you the picture, 73 degrees here, and they said, what's the angle in lucite? But they never asked about the zircon. The good news is, looking at this, we could skip layer 2 and directly equate these two and say that N1 sine theta 1 equals N3 sine theta 3 and solve for theta 3 without ever solving for theta 2, and we still get the right answer. And also that shows us why, if you equate these two, we get the original angle because we have 1 sine theta 73 equals 1 sine unknown. Well, obviously that's 73. So a lot of patterns when you look at the equation in its totality. All right, so let me create a pause to give you a chance to copy these notes down. Okay, so that is multi-layer refraction. So again, you have to know the concepts, and maybe that's all you need to know. And that means that wherever the index is the smallest in all those layers, the angle will be the biggest, smallest, biggest. Wherever the index is the greatest, this is the biggest, the angle ends up as the smallest. And then all the ones in between you kind of estimate, so that's the concept. The calculations, of course, you just use Snell's Law repeatedly. All right, so that's it for today. I hope you enjoyed the video. I hope you enjoyed the physics. I'll see you in the next physics video.